Section 13.2, line integrals, video 3. Before we get to actually evaluating any line integrals, I think it would be a good idea to review some common parameterizations. In other words, if we have a curve, how can we define it parametrically? Very common curve is a circle or parts of a circle. Recall that the equation of a circle is x minus h squared plus y minus k squared equals r squared, where h, k is the center and r is the radius. A common parameterization of a circle is to define the x function as x of t equals r cosine of t plus h, and to define y of t as r sine t plus k, where t ranges over the values 0 to 2 pi. This actually isn't a difficult parameterization to remember if you know what happens when you substitute these functions in for x and y. If you substitute r cosine t plus h in for x, the h's cancel and the rest gets squared. And if you substitute r sine t plus k for y, the k's cancel and the rest gets squared. So when you square these, you have r squared cosine squared plus r squared sine squared. Factor out the r squared, it leaves you cosine squared plus sine squared, which equals to 1. R squared times 1 is r squared. From 0 to 2 pi, it takes you one complete revolution around the circle. If you wanted only a semicircle, you could go 0 to pi. If you wanted a quarter circle, you could go 0 to pi over 2, or any other arc on the circle. Now, if your circle happens to be centered at the origin, then h and k are both 0, and your parametric equations collapse to this, in which case it's a little bit easier to see that if you square both of these and add them, you get r squared. And again, the interval of t values ranges from 0 to 2 pi, which takes you counterclockwise around the circle centered at the origin. There are ways to change the direction, and there are ways to start and end at different places. For example, if we switch sine and cosine, then we would start at the top and we would go counterclockwise. I invite you to explore that to make sure that what I just said is true. Another common curve that we're going to parameterize is a line connecting 2 points. Now, going all the way back to college algebra, there are ways to take 2 points and make the equation of a line. You find a slope, you set a point slope form, and then probably convert it to slope-intercept form. But in terms of parameterizing a line, there's also another standard way to do it, and I'll show you again for remembering it. The parameterization for the x function is 1 minus t times the initial x coordinate plus t times the ending x coordinate, assuming we're going from the 0 point to the 1 point. I guess I could have said 1 and 2 for first and second, but in the textbook they often refer to the first point subscripted with a 0. And then the parameterization for the y-coordinate is the same, you just change the x's to y's. 1 minus t times the initial y-coordinate plus t times the terminal y-coordinate. This one is also kind of easy to remember. If you just remember that one of the coefficients is 1 minus t and the other one is t. I say the word coefficient knowing that I'm misusing it there. And then remember that your parameter is just ranging from 0 to 1. What happens when you substitute 0 for the t? This coefficient becomes 1, that becomes 0, and you're just left with x0. But what happens when you substitute 1? It's the reverse. This coefficient becomes 0, that one becomes 1, we lose this, and we just have x1. So at the lowest value of t, this is equal to x1. At the highest value of t, at the lowest value of t, x0 is equal to x0. At the highest value of t, that's why they use 0 and 1 for the subscripts. At the highest value of t, x of 1 equals x sub 1, and then the same thing for the y's. Because there are no exponents, it is a linear function, and therefore the graph would be a line. The parameterization, the orientation, I should say, begins at the point marked x0, y0 when t equals 0, and concludes at x1, y1 when t equals 1. So it's an important one to remember. And there's also a way to generically parameterize any curve if it's defined by y equals a function of x over an interval of x values. The parameterization is to simply say that x is equal to t, and as a consequence, y is equal to f of t, and t ranges over the same values the x does. It's a sneaky way to parameterize a function, but it's actually pretty standard. And you could even do that if your function was, if x was a function of y, you would just say y equals t and x equals f of t. So these are some pretty common parameterizations you should be familiar with. How to parameterize a circle, how to parameterize a line, and how to parameterize any curve that's defined by a function, either y as a function of x or x as a function of y. I'll illustrate some of these in upcoming examples.